Hi, welcome to part 6 of photoelectric emission chapter. Okay, so this is from Jan 2015, YouTube photoelectric emission chapter. Now, so question number 15, Jan 2015. State what is meant by ground state of an atom. Okay, they asked what is a ground state. We know from the energy level diagrams we learned in our theories is that the ground state is the lowest energy an electron can have. Okay, electron at lowest energy level. Okay, so you have to write electron. Okay, ground state is electron with lowest energy level. Okay, so let's see what they wrote in the mark scheme. So lowest energy state of an atom or electron in lowest energy level, not with, electron in lowest energy level. So when an electron is present in the lowest, this is the most stable, remember this. Lowest energy level is the most stable. Okay, and electron can be in. Now, some street lamps produces a bright light which appears yellow. This light is produced by sodium vapor in the lamp. Okay, some street lights produce a bright light which appears yellow. So you must have seen the street light which appears yellow. Okay, now inside those light you have sodium vapor in the lamp. Okay, the graph shows the relative intensity of different wavelengths of light in the visible spectrum. Visible spectrum, they are talking about the light, the visible light. Okay, those are vibgyords and all produced by this type of street lamp. So these are the light, these are the intensity and different wavelengths of light this street lamp can produce. Now, this is a very commonly asked question. Explain why only certain wavelengths of light emitted. It's always like this, and it's always the answer is same. So I'm not even going to say you guys the answer. I'm going to just show you the mark scheme. All you have to do is by heart the mark scheme. That's it, and understand also. Of course, you have to understand. Okay. So remember, you know what they're asking? You're saying why only certain wavelengths? Why not unlimited wavelengths? Like this particular case, this sodium light. Why does only produce this light, this wavelength of light, this wavelength of light, this? Why can't it produce this? You know, why can't it produce unlimited wavelengths of light? Why only there are specific wavelengths it produces? Why not all of them? Okay, that's what they're trying to say over here. Okay, so now let's see what they wrote in the mark scheme. Okay, in mark scheme they wrote, first of all you have to say is that uh, electrons electrons are excited. Definitely when you have different energy levels, the electrons are excited, and when they are excited they go to higher energy levels, depend on how much energy they gain. If they gain low energy, they will go to lower energy level. If they get really high energies, they go to really high energy levels. Okay, so then they move to lower. Okay, so first of all electrons are excited, they go to higher energy levels. After they go to higher energy levels, they come down. Okay, they come down to their lower energy levels, and when they come down to lower energy levels, they emit photons. They emit photons. You have to say the energy is given out in the form of photons. So you have to learn this. Electrons, when they are excited, they go to higher energy level, they move to lower energy levels. You can even say they come to ground state, and when they're coming to ground state, they lose energy in the form of photons. Okay, now the energy levels are discrete, or only certain energy levels are possible. As I said, these are unique energy levels. They are not same from one another. One atom's energy level is not same with the another atom's energy level. They are unique, they are discrete. Okay, these are very important point. They have discrete energy levels. Okay, the energy of the photon, the photon which is getting released when the electron comes to lower energy level, this has a, okay, the energy of this photon is equivalent to the difference in this energy level and this energy level. For example, let's say the electron is coming from this energy level to this energy level. Okay, I'm sorry for that. Okay, so in that case what happens? In that case, the energy of the photon is equal to the energy of this, which is, let's say, E2, and energy of this, which is E1. So therefore the energy of the photon is E2 minus E1. You can just write energy of the photon is E2 minus E1. Remember, the answer for this question, why only certain wavelength is possible, is always an answer for this question is always this, and it's a very commonly asked question. These are the points you should learn. Okay, and there are only certain energy, limited energy differences that is possible, or only a corresponding set of frequency of wavelengths of light. Okay, so as only certain differences are possible, as electron can come from here to here, or here to here, or here to here, it's limited. Okay, the frequency is also limited, so you're supposed to learn this whole paragraph and come, okay, for the exam, because this is a very commonly asked question. Okay, now oh, not this question, where are the rest of them? Let me just see. This is question number 6. Oh yeah, it is same only. Now, a metal surface is illuminated with ultraviolet light of a single frequency. Okay, electrons are emitted from the metal surface. Definitely, this ultraviolet light has a energy more than work function. That is the reason electrons are getting emitted from the metal surface. Okay, it can be observed that electrons have a range of kinetic energy up to a specific maximum. Okay, up to a specific maximum. Explain how this observation provides evidence to support particle nature of light. Okay, so there is a range of kinetic energy up to certain maximum, not more than that. Okay, why is this providing support for nature of light, particle nature of light, rather than wave nature? If you remember the theory properly, in theory I actually mentioned that in wave theory, the intensity is directly proportional to the energy is directly proportional to intensity. Okay, so that means more intense light, okay, the more intense light hits the metal, the more energy the electron can gain. Okay, the more intense is it, the more energy the electron will gain, and electron can eject with any amount of unlimited kinetic energy, because there is no specific value the electron can absorb. Electron can eject or emit itself anytime it wants. All he has to do is just absorb energy. Okay, so that is the reason the electron will have unlimited kinetic energy, because intensity is directly energy is directly proportional to intensity. Now, but what happens in particle theory? In particle theory, there is one photon and one electron interaction is there. Okay, one photon and one electron interaction is there, and the electron has work function. Anything after the work function is getting converted to kinetic energy. Which formula? Hf is equal to phi plus half mv square, or kinetic energy. So kinetic energy is what? Kinetic energy is Hf minus phi. So that means after deducting the work function, how much our energy is left, that is getting converted to kinetic energy of the electron. So kinetic energy is very much limited. Okay, let's see what they wrote in the mark scheme. Okay, next question. So they wrote, okay, in energy with waves, energy could build up. I told you, intensity, energy is directly proportional to intensity. So the more the intensity of the light, more energy is getting absorbed by the electron. So the in waves, energy could build up. Okay, so any kinetic energy is possible. So electron can have any amount of kinetic energy. It is not limited at all. But what happens in particle theory? There is only one photon and one electron interaction. So since this is the formula, there is a maximum kinetic energy, there is a limited kinetic energy, because after work function, how much of our energy is left, that is converted to kinetic energy. I hope you guys understood this question answers. Now, then they said calculate the maximum kinetic energy in joules of the emitted electron. Okay, kinetic energy of the joule, kinetic energy in joule, we need to find the kinetic energy of an electron when the frequency is this, the frequency of the light is this. Okay, and your work function is this. Okay, so let's find, we know formula. When work function is given, when the frequency of light is given, we know E is equal to hf, which is equal to phi plus half mv square. Now here, instead of half mv square, I can write kinetic energy, because they are only asking kinetic energy, they are not asking the velocity. Okay, so now h I know 6.63 10 raised to minus 34. Frequency I know, that is 2.5 into 10 raised to 15. Okay, equals to work function. Now work function is given in 2.3 electrovolt. Can I do 2.3 electrovolt into 1.6 10 raised to minus 19? What I'm doing here is I'm converting electrovolt to joules. If you want to convert electrovolt to joules, you multiply electrovolt to, because 1 electrovolt is 1.6 10 raised to minus 19 joules. So 2.3 electrovolt is 2.3 into 1.6 into 10 raised to minus 19 joules plus the kinetic energy. Now you have to do this and you have to get an answer. Let's do this in the calculator. Okay. If we do this in the calculator, let's do this in the bracket itself. Okay, we can minus it. What is it? 6.63 into 10 raised to minus 34. Sorry for that. Be very careful. Into 2.5 10 raised to 15 into 10 raised to 15. Okay. The whole thing is this minus 2.3 into 1.6 2.3 into 1.6 into 10 raised to minus 19. Okay, how much are we getting? We are getting 1.3 10 raised to minus 18 is our kinetic energy. Let's see, is it 1. It is 1.3 10 raised to minus 18. Wait, I'm coming. I hope you guys understood the answer for this question as well. Okay, so this is another question from Jan 2012, Unit 2. It is GCE. Jan 2012, Unit 2, GCE. Okay, so they have a solar panel being used to produce electricity. Now the solar panel has an efficiency of 15%, so it is 15% efficient. The average radiation flux, with radiation flux they mean intensity. Radiation flux means intensity falling on the panel. So this is we know this. Okay, assuming that this radiation falls on the normally on the panel, calculate the area of the panel that would provide an average power of 500 watt. I think it's pretty straightforward question. You know intensity is power by area. Intensity is 210 watt, but we know it's only 15% efficient. So okay, average power output, calculate the area of the panel. It's only 15%. Okay, so out of this 210, it's only 15%, right? 210 into 15 divided by 100. That is the kind of power intensity it is falling on this thing. It's only 15% efficient. Okay, so out of 210, 15 divided by 100, intensity is equal to power by area. No, let me find the intensity. Let me break down the problem. If I do it directly, you guys will not understand. So intensity is 210 into 15 divided by 100. So how much is it? It's 31.5. Only 31.5 watt per meter square is falling on the panel. Okay, so intensity, how much is the intensity over here? Intensity we got power is 500 watt. Okay, and area is uh, okay, is it length into breadth or anything like, okay, they just, okay, just calculate the area. Okay, so area is 500 divided by 31.5. How much is that? 500 divided by 31.5. 500 divided by 31.5. So it's 15.87. So 15.9. Three significant figure. 15.9 meter square. Let's see what does the mark scheme say. So the mark scheme says around 16 meter square. Okay. So this answer is correct. Let's go to the next question now. Next question is it? Let me just check my textbook. Where is it? It's in page number 20. So let's go to page number question number 20. 1920. Okay, I think I already explained regarding gold leaf electroscope in the tutorial, the first videos or the second videos it is there. Most probably first videos it is in there. Now, the gold leaf electroscope is used to detect very small amount of charge. When the electroscope cap is negatively charged, electrons spread along the metal rod. Okay, and the gold leaf, so that they both are negatively charged. Okay, the rod and the leaf repel. So basically, when this both become same charges, they repel. So that's what they're trying to say. So this is how we know whether this is how the charge rod looks like. This is how the charge rod looks like, and this is how uncharged rod looks like. So a gold leaf electroscope can be used to determine the photoelectric effect. A clean zinc plate is placed onto the cap. Zinc plate, clean zinc plate. Okay, electroscope and the plate and are charged negatively. Electroscope are charged negatively. Okay. Now, so this is a negatively charged electroscope. If you shine ultraviolet radiation, you know ultraviolet radiation will eject electron from here. Na? So as the ultraviolet radiation will eject electron, the electron from the bottom will travel to the top to take its place. So bottom side, the number of electron at the bottom side will decrease. So the deflection here, the repulsion over here will decrease as well. Okay. So now the gold leaf slowly falls. That's what I said. Explain with reference to the work function of the zinc why this happens. You have to say the photon, incident photon has energy equal or more than work function. Okay, so therefore the electron gets emitted. As the number of electrons at the plate will decrease, electrons from the bottom rod will flow up to take its place, and as the number of electrons at the bottom decreases, the repulsion decreases. Okay, so the gold leaf falls slowly. You have to, I said regarding work function of zinc as well. You have to also say regarding most probably one-to-one interaction. I'm not sure about that. I will explain to you the 4 marks. Let's see what is the answer they got. It's question number 20. Okay, they said photons. Okay, photons are small packets of light, or light arriving in small packets. Okay, yes, energy of the photon is greater or equal to work function, results in electron getting emitted. Yes, so the electron loses charges or charge decreases and the leaf falls. I said almost all the point except for the first one. What are photons? What are photons? Photons are the light particles that arrive in small packets. Arrives in small particles. They are light particles that arrive in small packets. Okay. Let's go to the next question. Why is this effect not observed if the ultraviolet radiation is replaced by visible light? Because you have to say the energy photon of the visible light is less than the work function. So no emission of electron takes place. So energy of the photon here, energy of photon, okay, of visible light is less than work function. So no emission. No emission of electron. Okay. So photon energy, visible light is less than work function, or the frequency is less than threshold frequency. Any one of them you can say. Now, then they said ultraviolet radiation of wavelength 2 into 10 to the power minus 7 is shown onto the zinc plate. Calculate the maximum speed of the electron. So you have the wavelength, okay, and you have to find the kinetic energy. There is only one formula for kinetic energy in photoelectric emission, that is this. Okay, because from kinetic energy I can find the speed now. Okay, but here wavelength is given, not frequency. So remember, the same formula can be written like this: hc by lambda is equal to 5 plus ke. Okay, so what is h? H is 6.63 into 10 raised to minus 34. What is c? 3 into 10 to the power 8 divided by wavelength, that is given to us 2 into 10 to the power minus 7. See, they kept it in almost like 3 significant figure or so. Okay, so these are the 3 significant figure. Your answer should be also in 3 significant figure. Okay, equals to 5. Work function they gave us, how much is it? 6.88, 10 raised to minus 19. Don't write in this region. Minus kinetic energy. I hope you guys can see that. Let me just bring this a bit. Yeah, right. Just show you guys. Okay. So now, so what else is? Let me do this in calculator. This particular thing. Let me do this in calculator. So sorry. Something is wrong. Just wait for me. Uh, unpin. Oh God. Ah. Okay, so finally it is repaired. Okay. Let's say, okay, let's do this. How much is it? 6.63. 6.63 into 10 raised to minus 34 into 10 raised to minus 34. You know what? Normally I give brackets. It's better to give brackets in this kind of situations, okay, when you have lots of powers and stuffs. Okay, makes your calculation a lot accurate. Now, how much is it? 3 into 10 to the power 8. 3 into 10 to the power 8, close bracket. Okay, divided by 2 into 10 to the power 7. 2 into 10 to the power minus 7. Okay, so I'm getting around, how much am I getting? 9 point, how much is it by the way? 9.945 10 raised to minus 19. 9.945 into 10 raised to minus 19. I hope the calculator stays in the screen when I'm writing the answers, but it doesn't happen. I don't know why. Okay, so equals to this now minus 6.88 into 10 raised to minus 19. So there is your kinetic energy. So let me minus it with answer minus bracket 6 point, always give brackets, 88 into 10 raised to minus 19, close bracket. Okay, so 3.065 10 raised to minus 19. So kinetic energy is 3.065 into 10 raised to minus 19. Let me see my answer till here is correct or not first of all, then I'll go ahead. Here 3.07 10 raised to minus 19. Yeah, it is correct. Okay, now we have to find the velocity of the electron. Now kinetic energy is half mv square. So whatever I got here, 3.065 into 10 raised to minus 19 is equal to half mv square. Now mass of the electron is given below here near the question paper. Question paper last, the mass of the electron is given. Yeah, in the formula sheet. So this is mass of the electron, 9.11 10 raised to minus 31 kg. So 9.11 10 raised to minus 31 kg. 9.11 into 10 raised to minus 31 kg v square. So all I have to do is just multiply this with this and divide with this. Okay, if I do cross multiplications and all. So let me do that. So whatever I got multiplied by 2, okay, divided by mass of an electron, that is 9.11 into 10 raised to minus 31, okay, equals to root of the answer. How much is that? The speed is around, how much is it? 820. Like, let's just make it into three significant figure. 1 2 3 4 5. 8.20 into 10 raised to 5 meter per second. I hope that is the answer. Yes, it is. Okay, so done with this question as well. Now, the source of the ultraviolet radiation is moved away from the zinc plate. So if you move something away from the this thing, if source is moved away, its intensity decreases. Okay, remember that. Like if you have a torchlight, if you move it away from your eyes, the intensity of light which you feel is going to decrease. State what will happen to the maximum speed of the electron. The maximum speed of the electron will not change. If you take it away, your intensity decreases, the number of electron emitting decreases, but the maximum speed of the electron will remain the same because the frequency is same. Justify your answer. You have to say it remains same, remains constant, or you can just say same. Why? Because frequency is same, frequency of light is same. Okay, intensity decreases, remember that. If you take the light source away, intensity decreases. So let's say no change, it remains same. Photon energy does not change. Okay, photon energy depends on wavelength. Okay, so remember, frequency of the light remains the same. Okay, the photon energy does not change, photon energy remains the same, and photon energy depends on wavelength, frequency or wavelength. Remember, if the frequency is same, the photon energy is also same like before. I hope you guys understood this question as well.